Welcome back, ladies and gentlemen. We're going to be continuing with the solvation process and the heat of solution. There's a lot of weird words in there. Solvation process, heat of solution. What are we talking about? Well, solvation has got sol in it. Sol meaning solution. So solvation is the process by which we make a solution. Heat of solution. Heat is a weird word in this case. Heat, in chemistry, we kind of use that just to mean energy. We usually use the word heat instead of energy because we're used to thinking of heating something up in order to make something happen. So usually it involves some kind of, fire, because chemists like fire. Fire is fun. What can I say? Best chemistry changes color and burns. So fireworks, pretty awesome. Okay, let's take a look in some detail. What we got here, solvation occurs when a solute dissolves in a solvent. So the process of making a solution is called solvation because we want to keep using that sol word over and over again. When a solute dissolves in a solvent, the individual particles of the solute separate from each other, right? So, for example, here we go. We got ourselves a particle. In this case, it's a marker. And when I put it inside of the liquid, the particles of the marker have to separate. They have to physically get farther apart. I don't think that's a big surprise. What's probably more of a surprise is that then they sort of slide into the spaces between the solvent particles, right? When you dissolve sugar in water or salt in water, you don't see the salt or the sugar anymore because it slides in between the water particles and hides there. It sort of disappears. This is why we give it the word dissolving. It's a special word to describe what's happening, right? Nothing is disappearing. It's not like it's, being destroyed. It's just sliding. It's hiding. It's like hiding in the grass or between the trees, something like that. Anyway, for this to happen, the solvent particles, right, so the water, must collide with the solute particles. And the force of attraction between the two has to take hold. What do I mean by that? Well, again, picture, right? I've got my markers. In order for the water, which we'll use my hand as an analogy, to make one of these markers disappear from the rest of the solid, I have to first get close to it, grab it, and pull it away. Right? If I grab over here, nothing happens. If I grab it but don't hold on, nothing happens. So there's a series of steps that must happen just through sheer logic. Okay? Now, on the plus side, we know all of the individual pieces of these steps. Why is the water getting close? Because all particles move. We learned that in kinetic molecular theory. Why do they grab onto each other? Intermolecular forces. So the intermolecular forces between the water and the solid, in this case my fingers, grab hold. Why do they then pull the thing away? Again, random motion. All of this is stuff we already know. We're just applying it to a solution. So solutes, right, would be salt. Solvent would be water in this example. All right? Okay. The heat of solution. So we've explained what solvation is, but what is the heat of solution? What does that mean? Well, again, heat is energy. So the energy of solution. Sometimes also called the heat of solvation, the energy of making solutions. That probably makes a little more sense, doesn't it? So when the attractive forces are broken, so again, in our analogy, that's when I took this and went, energy is required. I think that's no surprise, right? If I want to break intermolecular bonds, I need to use energy to break them apart, to overpower them, to overcome them. Therefore, the separation of solute particles from one another and the separation of solvent particles from one another are both endothermic, aka they take energy to happen. Put another way, again with the analogy, I've got my markers in the basket. The water is going to grab a marker, take it away. Well, in order for that to happen, the water has to go from being near other water to being like, hey, what are those markers over there? I wonder what that is, and go to grab it. Well, in order for it to go grab it, it has to break free of the connection with the other water particles. That takes energy. Once it breaks free, it goes, it grabs one, intermolecular forces, kinetic molecular theory, pulls it away, and wanders off. Maybe it brings it over to its friend, and then it hides in between, right? It disappears. But maybe it doesn't. Maybe it takes it somewhere off by itself. And then this water's like, what am I going to do? Well, I guess I'll grab my own. Now I got my own friend. Right? So it's a process that takes energy, one way or another. However you do it, you're going to need energy. The attraction between the solute and the solvent is exothermic. What do I mean by that? Well, remember, Breaking bonds takes energy. So breaking the connection of these guys takes energy. But when they grab something, a grab is a new bond. New bonds release energy again. So the process of breaking an existing bond, takes up energy, and then grabbing a bond, making a new bond, releases energy. So it's like, if I want to break free, $10. You got $10? Fine, you break free. Making a new one, I'll pay you $5. Oh, I didn't really make money there, did I? $10 to break free, $5 to make a new one? I'm down $5. Of course, could be the other way, right? Could be $10 to break free, $20 you make a new connection. That'd be nice. Decent combo. Could you imagine if I got paid $20 every time I picked up a marker? Man, I'd be rich. All right, so bond breaking needs energy. Here's a good example. All right, this can't break until, boom, energy comes in, it breaks. When I make a new bond, energy comes back out. Bond forming releases energy. Now, if I was breaking and making the same bonds like this image is doing, well, it's the same energy going in and out, right? And to be fair, something like this probably happens all the time because, again, matter is complicated. But if I'm dealing with, say, breaking one bond and making a different bond, the amount of energy involved could be a different number. And that is our heat of solvation or heat of solution. Okay? So, whenever energy absorbed, whether energy is absorbed or released in the overall net process, net in this case just means total, it's a math term, of solution formation depends on the balance between these two processes, right? Basically, do I use more energy breaking the old compared to making the new? That's the question. If I take more to break and I get less, then overall that took energy. If it's the other way around and I break the bond and it doesn't take very much and then I make a new one and I get tons, then overall I gain energy. Right? So the net change is called the heat of solution or the heat of solvation. And again, yeah, net is total. So here's kind of the steps that we're dealing with in pictorial form. You've got your cube of some solid in this case. Let's say it's salt. The first step is I got to expand that. I got to spread it out. Expanding, breaking bonds takes energy, right? This is going to take energy. Down here, the solvent, the water, has to expand as well. I gotta have enough space to put all of these red ones in between the blue ones. That also takes energy. So these two steps take energy. You gotta put money in. Step 3 over here, where you mix them all together, releases energy again. So if step 1 and 2 takes up more than step 3 releases, then it's going to be endothermic. Oh, I almost said the wrong one. Endothermic. You're going to have to take energy in. On the other end of the spectrum, if these two use less energy than I get out, this whole thing will be exothermic. Okay? All right. Hopefully that makes sense. Endothermic, if the amount of energy absorbed is greater than the amount of energy released, then the overall solution is endothermic. I literally just said that. Here's an example. If I want to break this down, it's going to take me some energy to break it. This would be a cold pack, right? You've seen one of those, right? You've injured yourself and it hurts, right? You go and you get this like thing out of usually gym has them and such, and then you like crack the chemicals inside and it does a chemical reaction, and the net result is that you end up absorbing a bunch of heat in order for that chemical reaction to occur. That heat being absorbed means the thing feels cold, right? We talked about that in physical properties. Now, there's a video. I have a secondary video that I recommend you watch on this. It's actually a pretty good one, so I recommend you take a look at that, but that's about all I'm going to say on it. Exothermic is the opposite, right? The amount of energy absorbed is less than the amount of energy released. So then the overall solution becomes exothermic. Here's another example. This one here, breaking apart into two different pieces, into an aqueous solution, releases heat. This is a hot pack. It's the opposite, right? This is what you do. You get these, you stick them in your pockets in the cold, right? And you turn them on, you activate them, and they heat up, and that gives you the ability to keep your hands warm. Okay? All right, so what are we seeing overall? That's it. There's not much for this one. The process of breaking bonds always takes some energy. Making new bonds will give you some energy. The question is whether or not the whole process of breaking the old and making the new, does it overall take energy or does it overall give energy? We call that the heat of solution. So with that, you guys can do a little bit of practice, and I will see you guys next time.